All right, everyone. Welcome to another episode of the TWiML AI podcast. I'm your host, Sam Charrington, and today I'm joined by Vinesh Sukumar. Vinesh is head of AI ML product management at Qualcomm Technologies. Before we get going, be sure to take a moment to hit that subscribe button wherever you're listening to today's show. Vinesh, welcome to the podcast.
Thank you, Sam, for providing me the opportunity to be in your talk show.
I'm super excited to jump into our conversation. As we all know, AI has been evolving very quickly, and we're going to dig into how that evolution is impacting AI at the edge and the various use cases that are supported by edge technologies. Before we dive into that topic, I'd love to have you share a little bit about your background and how you came to work in machine learning and AI.
Yeah, sure, absolutely. I've been, in the AI space for, I would say, give or take about 10, 15 years. Started my career working for Jet Propulsion Labs. In those days, was mostly looking at, you know, image classification, object classification, but under the nomenclature of computer vision. And those days, it was all about looking at big charts and able to classify content based on the captures. With time, transition more towards consumer electronic field, mobile cell phones, working on cameras, and then with time, transition over to PC platforms, and then to automotive platforms, and then finally at Qualcomm had the opportunity to look at AI ML more horizontally across many verticals from mobile all the way to automotive. And the challenge with AI is what today is obsolete tomorrow. So you need to be a student at heart all the time and learn new things, and that keeps me quite interested while working at Qualcomm.
Well, I think that theme of change is going to be a big one in our conversation. In our previous chat, one of the things you mentioned that struck me was just how the evolution in uh, use cases and deep learning architectures, as just a couple of examples, all these things impact the hardware architectures that are used to support these kinds of use cases and technologies on the edge. Can you talk a little bit about what you're seeing from a use case evolution perspective?
Yeah, absolutely. A great question, by the way. Historically, when you look at AI ML on the edge, to a large extent was quite small in nature, was very much evolving around image and video, wherein you want to look at image enhancements, image modifications, background segmentation, classification, detection, those kind of use cases. But as the technical acumen, a lot of contributions from research scientists, ecosystem acceptance of AI started to morph, you could see that the evolution of AI use cases started touching other modalities, from image and video, moving on to text, moving on to linguistics, moving on to commerce, and many other segments. So, as such, when you put this totality into picture, historically, to a large extent, all the AI algorithms was mostly convolution heavy, which was mostly reflecting on CNNs, because it was quite good in nature at that point of time. But as you get in more modalities into the picture to support use cases or create key experience indicators, now the investment is moving towards, I would say, transformers as an example. Then moving on to generative content, which has been quite a lot of interest these days. Recommendation engines, which has been quite popular in social media and in commerce platforms. The question really becomes: is your architecture a uh, generic enough to be able to support new and upcoming architectures? Is it only meant for for convolutions, or can it go beyond convolutions into complex architectures like large language models and recommendations engines, which have been quite popular these days? And or do you want to focus on architectures which can do very specific tasks? They have been excellent in performance, excellent in power efficiency, those kind of stuff. So these are some of the questions and debates we ask ourselves. We try to enable both, and depending upon the vertical of interest, vertical I meant as a specific form factor of interest, could be mobile in nature, could be automotive in nature. We try to make sure those investments kind of scale accordingly.
Yeah, I'd love to have you kind of dig into some of those trade-offs. When I think about what I know about the way Qualcomm approaches enabling AI on device from many prior conversations, one of the themes is really understanding the architecture and optimizing around that architecture, which as you're suggesting here, maybe an architecture or maybe a device has some special accommodation for convolutional neural networks that allows them to operate really quickly and with a lot of efficiency, and then the predominant architecture shifts, and um, there's something else that you need to think about. At the same time, a lot of the conversation around optimization is at a, a bit of a lower level than that. Optimizing matrix multiplication and things like the resolution of your integers and things like that. So maybe talk us through kind of how you've approached the balance in the past, and when a shift like this happens, do you just optimize around the new thing, or are you kind of creating something that works across the new and the old?
Yeah, that's a fair question. This is something, we get constantly challenged by our partners as well. So historically, the way we try to approach these use cases or applications is we try to understand what are the key performance indicators. There could be applications which are anchored on latency, anchored on performance, anchored on quality of service, anchored on power efficiency, or all the above, right? So as such, when you have a certain use case, you try to get into certain system decomposition. The decomposition really means is if I invoke a certain application, I'm able to meet the KPIs of interest at an application layer. That kind of answers the question by itself: is what is needed from a software perspective and what is needed from a hardware perspective. um, Now, the hardware is obviously a little bit more challenging, is because we want to kind of think 2 or 3 years in advance, right? To really, do we have the right investments in place to really push for it? And software is a constantly evolving topic, to say what kind of optimizations is necessary at the library level, at the kernel level, at the compiler level, to be in a position to generate machine readable code that is easy to execute. So let's start off with, on the hardware perspective. From a hardware perspective, I would say some of the key most important elements is, do we have the right data types? In Qualcomm's perspective, our position and push has always been, we want to move towards fixed point, as we believe it gives you the highest performance, quite uh, leadership class power efficiency, and also a very small memory footprint compared to that of a floating point representation of the same model. So as such, we continue to push the boundaries of where we invest in data types. Historically, it was float, and then we transitioned to int8, and we're now moving towards int4 representation, right? So that's one perspective. The second thing is, what would be the investments necessary from a compute standpoint, from a local tightly coupled memory standpoint, with the expectation that you could, store the bias functions within the tightly coupled memory rather than making round trips to DRAM, because you want to save on power efficiency, as an example, right? So there's always a question of what kind of compute is actually the right amount of investment. So here we start looking at use cases and then try to understand what is the state of art architectures really supporting those kind of use cases, right? And then we try to construct the investment in compute around that. Now, last but not the least is elements around bandwidth. Do we have compression schemes that would really push for high inference per second? How is the register spacing established? What kind of sparsity or intelligence needs to be established as part of the hardware, so that you don't really spend cycles of time in trying to do zero-based computations? So all these are feature enhancements that we really push for, from a hardware perspective, to really drive for leadership. Then you go towards the software level. Now, software level is obviously complicated. Here, we can start off with quantization. Quantization is a metric that we heavily push for, wherein we can actually provide the opportunity to our partners to transition towards, fixed point in 8 bits and 4 bits for both activation and waits. So, we have a tool called AMIT, and we're putting a lot of energy on AMIT, which is artificial intelligence model efficiency toolkit, that provides the flexibility to our partners to not lose on accuracy while getting higher performance, right? Then we move on to our AI stack, which we recently announced in a couple of months ago last year, which we call as a Qualcomm AI stack. And as part of it, we have the runtime, we have tools, we have libraries, and the low-level API structure that is flexible enough to execute this model or desired application on various OS. Could be on Windows, could be on Linux, could be on Android, those kind of subsystems. Here, there's a lot of emphasis on how do we optimize on performance. Now, performance is a very broad term, so we look at, if I happen to have concurrency, how can I pack a single graph that is made up of composite smaller graph into into our hardware mechanics, and then execute them, as an example. Second thing is, if I have to securely store the model, in this case, what kind of encryption schemes needs to be supported to make sure somebody doesn't hack into the model of interest. The other could be is, what kind of preemption schemes I would have if we happen to have concurrency. Can I support all these graphs simultaneously without compromising on quality of service? So all these are investments that we really push for, working with our engineering staff. These features get updated on a regular basis to really make sure we can push for much larger deployment of applications which are quite complex in nature across all BUs. And the one good thing is, since we have a unified Qualcomm AI stack that works from mobile all the way to automotive, the lessons learned from automotive get propagated to mobile, and from mobile get propagated to auto as well. That way, there is a lot of handshake of good information. That way, the applications can be deployed across all form factors with ease.
You mentioned mobile and auto. What are the specific use cases you're seeing in each of those domains? As this shift from convolutions to transformers takes hold, are there any in particular that jump out as kind of driving the trend?
Historically, when you look at mobile as an anchor point, when you look at it as a consumer buying pattern, to a large extent, people are buying phones because of good camera. So, which means most of your AI analytics is revolving around image or revolving around video, right? So they are to a large extent convolution heavy. Now people are slowly, trying to bring in text as an input and then fuse image with text, where transformers is becoming a quite an important element of interest, and then try to see, can I use the sequential data that is embedded as part of a transformer network to understand context and make a much better prediction. So we kind of, revolving around text or an image and quality, but with different classes of networks, which are not necessarily convolution heavy, but more towards transformers, right? So that's, I would say, to a large extent, um, an anchor point for mobile. Now, obviously, in mobile, there's a bigger challenge is, it operates on battery. So our expectation is we really give this performance at much lower power, so that you don't drain the battery as much as possible and have a much smaller memory footprint, because you're operating within a mobile device. But as you move towards automotive, it's a completely different space. Here, concurrency is a big deal. You're trying to work with 15, 16 different sensors. Could be camera sensors, LiDAR, radar. How can you fuse them together to actually provide you a quality of service? Latency is a much bigger deal. Here, the physical input tensors or the resolution of the camera is much bigger, right? Either you have 1 megapixel, 3 megapixel, 5 megapixel, 8 megapixel. And on the mobile side, the input tensors are very small in nature. They're probably 512 by 512, 256, or 225 by 225 kind of scenarios. But on the automotive side, because you need to have a much larger field of view, you want to make predictions or decisions much more stringently, you take a much larger input tensor. So the physical compute requirements is much more intensive compared to that of what you would see from a mobile environment standpoint. And not to mention is, you're going to see also the ask for one deep or one AI model that does multiple stuff. It could look at a drive policy as an example. It could look at parking stack as an example. But you have the same infrastructure to really make a lot of those predictions. So a different set of challenges from an automotive standpoint compared to that of mobile. But having a unique and I would say a consistent stack both on the mobile and automotive front has really helped us really accelerate, I should say, new operators, new complex models, so that our developers can really use this investment and then drive innovative applications.
When you speak about the compute requirements on the auto side, I'm wondering if you are familiar with this. I saw an article just the other day that referred to an MIT paper that uh, they did an analysis, a high level analysis, but the conclusion that they came to was that at full deployment of fully autonomous driving, when the dominant mode of transportation is autonomous vehicles, they projected that the compute requirement uh, was pretty much on par with all of the data centers today. Have you seen that paper by any chance?
Not necessarily, but I think in the gist of what they're probably claiming, as you're suggesting, is the compute requirements within ADAS space. Historically, when you look at automotive, there's an infotainment side, which is purely in-cabin entertainment purposes, and then there's an ADAS side. ADAS obviously goes by L1 to L5, depending upon the levels of autonomy.
Right, and I believe they were specifically referring to getting to full distributed fleet of level 5 autonomous driving fleet.
Doing that to a large extent, having both infotainment and L5 level of autonomy services is quite complex in nature. And one layer on top of it is the fleet management. Is how can you have multiple trucks, as an example, or multiple robo taxis being efficiently managed from one control center, and all this information handling is going to be quite complex. And I wouldn't be surprised, if you're really looking at an infrastructure that powers the data centers today, because I think that's where you're going to go towards, as fully autonomous vehicles or fleet management takes a little bit more, I would say, broad acceptance by, I would say, by consumer space.
Yeah, so it sounds like that doesn't that level of scale required, doesn't surprise you given what you know about ADAS and those requirements.
Absolutely. I think we've been doing that to some extent historically as well. And you look at our history, we started off small with a much smaller footprint occupying in the mobile space. With time, for the last 5 to 6 years, we've kind of expanded to adjacent business units. Could be AR, VR, compute, IoT, and automotive. And with each adjacent BUs getting a lot more traction in AI, the requirements have actually scaled up much, much more than than we had expected. So to answer your question, we've been surprised, not necessarily. We've been planning all along. We just have to make sure is the time to market, the time to really accelerate solution deployment can really be much more faster, because the rate of innovation that's happening, for example, in automotive space is enormous, right? I see a lot of L2, L3 kind of vehicles coming out this year and next year, as people start transitioning to level 4 and level 5, which is full autonomy. At that point of time, do we have the necessary infrastructure to take actions based on the compute investments and software investments we're going for it? And that's what we've been trying to push for to make it happen.
Yeah, so we talked about mobile, we've talked about automotive. A third area that historically has been interesting for edge use cases is enterprise and kind of distributed, things like distributed cameras. Is that still an interesting use case or a growing use case?
Yeah. So when you look at form factors as such, um, automotive is one extreme. Enterprise could be seen as something like a PC compute devices, as an example. Could also be seen as personalized devices like wearables, hearables, as that market takes over. And PC as a form factor is gaining a lot of popularity within the enterprise segment for good or bad reason post COVID, only because work from home has become quite important. And the need for AI in PC is just soared post the pandemic situation. Uh, few examples in this case would be, how can I improve video conferencing, as an example? How can I improve streaming, as an example, within the enterprise space as well? In streaming, historically, when you look at it, there's been enterprise streaming, game streaming. Enterprise streaming always used to be on a reference platform, but post pandemic, now people want to be doing it from their own homes. So the question has really become is, are we in a position to support an infrastructure that supports enterprise streaming? And what kind of form factor will push for it? And and PC has been a fantastic form factor to really drive it. And most of our engagements moving forward, you're going to see a lot of big announcements come from that front, and how we really positioning, um, I would say, PC as a form factor to drive enterprise scale experiences.
That's interesting. I hadn't thought about the, the PC, um, experience in that question, I was mostly thinking of these use cases like, I guess, what you might call more embedded use cases like distributed cameras and distributed sensors and that kind of thing. Do you see a lot of growth in those use cases?
Absolutely. I would probably position it this way. When you look at AI inferencing to a large extent, is very generic in nature. Uh, what applies for me applies to you in any given context. There is no personalization element to it. So the question really becomes is, can I collect more data about the user to drive personalization? And this could be coming from sensors registered to the user, could be cameras registered to the user. As such, if I get more pieces of information, it could be visual in nature, could be textual in nature, could be audio specific information. Can I make that inference on the edge for the user more optimal? Right. And this is something that's gaining a lot more popularity. But the biggest challenge has been, as part of this use case enablement, is how much data is good data? What data is good data? Uh, how do I enable some level of uh, supervision to make sure the data that's been collected is also labeled properly? Because if we don't have labeled information, I can't engage in retraining. If I have to do retraining on the edge, what kind of constraints I would have on the hardware and software side to be in a position to encourage learning or retraining? So, all these big questions usually come up, and the ecosystem in general is trying to understand is how can they scale moving forward. And this is, one such fantastic example is collecting the right amount of data and then driving towards personalized inference moving forward.
Interesting. That touches on themes of data centric AI, which is a big conversation in the industry, kind of shifting from masses of lower quality data to small amounts of higher quality data, and putting a lot of care in place around how that data is curated, so as to make more efficient use of it in training and tuning, which seems right in line with the kind of thing you'd want to worry about if you're dealing with edge type devices.
I would say absolutely. Industry as such is kind of morphing away from a model centric view to a data centric view. But as you transition to a data centric view, the question really becomes is, can I have investments across the entire picture of MLOps, from data annotation all the way to data monitoring? And especially on the edge, if you're going towards more user based personalization, it's extremely critical to have elements of collecting the right data, labeling it, filtering it, and training on the edge. And then once you enable inference, you want to also monitor it. Are you seeing some kind of drift? What kind of drift are you suggesting? And can I make any compensation based on the drift? So yes, absolutely becoming more critical. How we go make it happen on the edge is always a big question mark, because the physical structure of edge devices is very different. Not all devices can support it, and the question really becomes is, can I run partially on the cloud? Can I run partially on the edge? But these are big questions that the industry is facing today, and I'm pretty sure in the next 6 to 9 months we'll have opportunities out there where people are going to say, guys, AI is actually becoming more meaningful to me, because now I'm engaging in more an extensive MLOps investment rather than a very toned down, generic, with no common sense AI inference that exists today.
When you think about what that MLOps footprint looks like, kind of this edge aware MLOps footprint, what's different about it from the way folks are doing MLOps kind of in non edge environments?
So when you look at the MLOps as it exists today, historically, uh, I would say two or three scenarios. One, you have a pre-trained model. The pre-trained model either has been available in open source community or somebody's already developed it. You take the pre-trained model, you quantize it, you fit it to the envelope of your edge device, and you invoke it, and you get it running. Now, there's a drift. You see drift over time. Nobody monitors it. Nobody cares about it, and it's already completed. The second category I would say is wherein you don't have a pre-trained model. You want to start from the beginning. And this is a classic example, like an infotainment use case within an automotive segment. An automotive segment, you want to look at, let's say, a driver monitoring system. You want to understand the emotional state of a driver to take certain actions, and maybe take control over him, because if he was not in the right state of mind, you don't want him to encourage driving. But understanding the emotional state of a driver means you need to understand or make accurate predictions. But for that, you need access to data. Today, you don't really have too many data points. So here, there's a lot more emphasis on creating synthetic data to kind of really create a scenario that would show the emotional state of a driver. Synthetic data was not popular, I would say, 3 or 4 years ago, but now it's becoming extremely popular because you don't have enough data to create the right model. So once you happen to have that, again, then you get a pre-trained model, you emphasize, you get it running, and you're fully functional, right? So the first two is, to a large extent, mostly popular in the industry today. But the third portion is, again, is how do I constantly learn? How can I make sure that the model I've developed from a synthetic data source or a pre-trained data source can evolve with time as I understand the user much more diligently moving forward? That doesn't happen. So the question really becomes, is how can I make it happen? I think over a couple of years ago, Tesla kind of introduced this fact wherein they used to take elements about the road and the scenarios that they're trying to evolve and work on, and then they used to send that to the cloud, optimize a model, and then invoke it back to the device. A similar concept. Google talked about it, what we call as federated learning, a couple of years ago. Similar concepts. But we're trying to say is, if that information which is very prevalent to the user, you don't want that information to leave the device. So what this infrastructure that existed before in the cloud, can I bring it to the edge and constantly make the model learn so that it commits less and less mistakes moving forward, and on top of it, can accommodate user specific information. So that's the big difference moving forward from an industry standpoint.
You spoke a bit about these metrics that you are tracking and caring about when you're looking at edge cases and trying to map them onto hardware architectures, things like latency and bandwidth and all these things. To what degree has do the each of these architectures kind of drive their own distinct usage patterns? Like, we used to think about the kind of the cloud as you want to kind of provision in a hybrid type environment, at least, like provision for your sustained usage locally and then be able to burst to the cloud for peak usage. Is there that kind of scenario or thinking in place when you're thinking about edge?
I would say to a large extent, when you look at edge, by definition, has a very wide footprint. The footprint could be in terms of compute, in terms of bandwidth, in terms of memory, in terms of power, which really would put a constraint of what kind of inference is possible on the edge. Right, so that's one thing. The second thing is, cloud to a large extent provides you a unified experience, meaning that no matter uh, where you are, as long as you have good connectivity to the cloud, you're able to get a certain inference profile. But the challenge is, you need to have that strong connectivity to the cloud. Now, the third scenario which you mentioned, some kind of combinations of hybrid, wherein can I run portions on the edge, portions in the cloud? Absolutely possible. To some extent, it already exists today. A classic example would be, if you're trying to do video conferencing, as an example, Blue Jeans, Teams, all these folks, when they enable language translation or language transcription, they really invoke automatic speech recognition, neural machine translation, and text to speech. These are heavy compute workloads, and most of them are resident on the cloud. The reason they're trying to be resident on the cloud is you want to be supporting multiple languages to be able to translate to English. So by definition, it's a very large library file which does not, really fit an edge envelope. So there are going to be these situations wherein you have to partition your workload between edge and the cloud. Now, the question for us is, people are working on the edge, is how can you make edge more competitive so that you can enhance user experience? And I'm pretty sure, as generative AI use cases, chat GPT like use cases become more prominent, the question only becomes is, should I be running these models on the cloud? Going to run portions on the edge and portions on the cloud, but these are all good discussion topics that is happening in the industry as we speak today to really drive that partition and make edge more relevant compared to that of the cloud.
Yeah, literally, as we're recording this, one of the things that is capturing a lot of excitement in the community is folks are downloading this new LLM, the Meta Lambda model, and running it on their local machines, their MacBook devices, and running a 7 billion parameter LLM and getting results in decent time. And I saw a post just earlier today about someone who ran this on a Raspberry Pi. Um, and I think this is an indication, an early indication, maybe that people are going to want to see these types of models running on device. And certainly, we're going to hope that the performance is better than the 10 seconds per token than the person saw on the Raspberry Pi.
Absolutely, absolutely. I mean, this is going to be inevitable, right? People are going to understand the fact is image to image translation or text to text translation, especially for complex queries. If it takes like 15 seconds to respond, you're not going to get the best user experience, right? So the question really becomes is, can I bring it somewhat manageable and can we get it done?
So, do we know what that transformer specific architecture looks like, and how it differs from the convolution tuned architecture?
Yeah, so when you look at large language models, by definition, is an evolution of the transformer itself. To a large extent, most of these models are kind of basically divided into three portions: the encode portion, the decode portion, and the unit portion. But in the expectation is, you can understand the context, understand the relationship between the sequential data that exists as part of the model itself, and make an accurate prediction, right? And as it knows more about the user, it makes a recommendation that's very fine tuned to you. And that's the reason Transformers has been quite successful in nature. And you can see a lot of evolution of many such architectures with which are like multi-layered attention kind of platform, because it actually is able to uh, provide an answer which is very relatable to the question you ask rather than a very generic statement. This is much more different than from a convolution heavy architecture, because convolution is more about, I would say, classifying, detecting, kind of stuff. It didn't really have any context, but it kind of exactly does manual stuff that you're asking it to do. Now, that being said, researchers are already in the industry working on making convolutions, or I should say CNN type architectures, much more intelligent, because it kind of solved a unique set of problems, but they're trying to understand, can CNNs get into context? I'm pretty sure with time you're going to see there. But as of today, you're seeing, once Transformers was introduced way long ago with, I think from Google, if I remember correct, and it has taken its own life for the last 5 to 10 years. And here we are with LLMs that are kind of banked on Transformers.
And so, do we know what that translates into from a target hardware architecture perspective? Meaning, as you noted, the convolutional networks, the focus is like speeding up matrix multiplications, right? The faster we get those, that's kind of all we need. Um, but now that attention is all we need, are there specific structures that you see evolving in hardware um, to accommodate attention? Are there registers that you might build into hardware that are attention specific, or kind of designed to accommodate unique properties of the transformer?
So the first thing usually you want to get into this picture is when you look at these Prometheus-style models, which are coming up from OpenAI team, they're like what 175 billion parameter kind of issues, and GPT-4 is releasing this week or next week. I'm pretty sure it's north of 200 billion parameters. So the question really becomes is, as you're trying to transition or bring elements of those models, or even Meta's Llama model, I think that you're referring to earlier, is around 7 to 10 billion parameter range. So the question first really becomes is, do you have the necessary memory to really store these parameters? Number one. Second thing is, as you start enabling on the edge, does your hardware support fixed point like int8 or int4, so that you can uh, not lose on performance, have increased performance with a much lower memory footprint? That would be a second point. The third thing would be is, do I have the necessary software to be in a position to really support quantization from a floating point version to a fixed point version? Right, that would be, I would say, a critical as we start looking at these large models. Last, from a hardware perspective, is, do we happen to have a certain amount of acceleration and programmability to support the encode portions, especially the initial layers of the stack, so that your inference time is much more elaborate. So I think these are some of the fundamentals, I would say, to really get it done. Apart from, hey, do we have the speeds and feeds in terms of a number of GOPS that's available to support it, the amount of bandwidth that can uh, uh, drive these transactions between memory and compute units. Those kind of stuff are pretty normal, but our expectation is you really need to have at least three or four key elements which I just talked about on the software front and the hardware front to really get these LLMs up and running on the edge. And I wouldn't be surprised in the next couple of years you would see major silicon vendors start enabling these large language models in some shape or form on their silicon.
Another thing that came up in our conversation that I found was pretty interesting is some of the work that you're doing around microtile inferencing. Can you talk a little bit about where that comes up and what's new there?
Yeah, absolutely. The microtile inferencing is something that we announced last year in our annual Snapdragon Tech Summit. And one of the points or elements of that focus of attention was, these days we have an opportunity to work with quite large graphs. And historically, when you want to load these graphs, you load this entire graph into our processing units, and then you try to run operations one layer at a time. So by definition, it consumes a lot of power and it takes a lot of time from an inferencing standpoint. So the question really becomes is, how can we intelligently accelerate performance, both from a latency standpoint, also from a power consumption standpoint? So what we did is we actually broke these graphs into smaller units called tiles. And we also have a lot of control processing units that can handle scalar, vector, and matrix based operations. All we had to do is to really make sure that we have the right control mechanics to be able to distribute these small tiles of graphs to accelerate performance. So this is what we call as microtile inferencing, is we having the ability to divide the graph into smaller units, and then activating the several control processing units that we have as part of a system to make sure we can give out inferences at a much faster cadence and time compared to the old style of reading one entire graph in its uniformity.
And just to be clear on the nomenclature, are we talking about um, a computational graph like a TensorFlow or PyTorch program, or a graph of relationships like you might process with graph neural networks?
Yeah, a good point. So this is not the graph neural networks like you would see in medicines, to understand DNA relationships kind of stuff. But this is like at a TensorFlow, a model, which I refer to as a graph. The model could be a single model, could be multiple models, but we construct the graph out of it, and then we execute the graph as a function of a TensorFlow or a PyTorch model, as you stated.
Got it. So, in a sense, you're kind of sharding your model or your program and operating on shards of the the model or the TensorFlow program.
That is correct. In a much more parallel fashion rather than a serial fashion, because we've been able to divide them accordingly into smaller portions or actually smaller portions of models or ops, and get them executed parallelly at the same time.
Yeah, it almost calls to mind kind of your traditional the kind of thing that you might do in supercomputing or kind of traditional distributed compute is you've got this program you want to be able to parallelize it. You kind of break it into smaller chunks and you distribute those to different machines. In this case, it sounds like we're talking about, well, I should ask, are we talking about devices or are we talking about cores, for example, on a single device or single processor?
We have, I would say, multiple small cores within the device itself. And depending upon the function that is necessary, if it's a vector based function, then a certain core gets activated. If it's a scalar based function, then a certain core gets activated. And something similar with the matrix based operations. So that way we kind of distribute it intelligently depending upon what kind of function is being invoked at a certain time period, and then execute those functions parallelly.
Got it. So it's not just kind of parallelizing across a homogeneous infrastructure. It's also specializing, is parallelizing or distributing it according to specialization and what that particular tile requires.
Absolutely, because many of the use cases, as we start looking today, is just not one model. You could have 5, 6, 10, 15 different models all needing to be executed at the same time. So it's quite important to understand what the mechanics of those models are, and then try to invoke it, without compromising on latency.
It almost sounds like you're running a micro Kubernetes on your on your chip and doing I forgot the name of the feature where you can kind of direct specific workloads with specific requirements to a particular pod.
Yeah, something like a cube flow, pretty much on the edge.
Yeah.
Exactly.
Maybe, just, briefly with maybe just briefly returning to this theme of change and evolution, any quick thoughts on where you see this all going over the next, I'll let you pick the time frame.
I would say, next 6 to 9 months is going to be exciting. Um, a lot of craziness around generative AI, around use cases that can be coming into that picture. So I wouldn't be surprised wherein, I would say AI 2.0 is kind of coming into picture, wherein people actually are seeing um, context into queries. They're able to understand for any given request that you might have, you're actually getting a response which is more tailored to you. So exciting times moving forward. Text to text, image to image, text to 2D, text to 3D. All kind of scenarios are going to morph. The other day I was kind of reading an article is when OpenAI came up with their models, more than 150 startups have actually pruned up in the last couple of months using their API. So I think exciting times, and we truly believe uh, you know end of the day, consumers or users are going to see fantastic new experiences which is just not there before.
Yeah, yeah, yeah. That's super interesting that you say AI 2.0. I've been saying AI 3.0. Uh, but it's clear that there is a N plus one happening somewhere, independent of where you started.
Yeah, my count starts from zero point 0.0, so maybe that's why I'm off by one.
Awesome. Well, Vinesh, thanks so much for taking the time to catch us up on AI at the edge and everything happening there.
Absolutely, thanks for the opportunity, Sam, and I hope to catch up with you in a different podcast very soon. Thank you.